Okay, now by the way, just to help with the accuracy of the shape, I tend to draw the asymptotes first, because that way you know your curvature will bend toward the asymptotes, which tends to be what people get wrong. So, whoop, that's a bit wavy, but it won't matter because the part I'm interested in is this side anyway. So, okay, so there's a standard hyperbola. They name a point P, and then they have a point P joining, a line P, a line joining P to the focus that's parallel to an asymptote. Okay, so that was a lot of words, right? So let's try and put a place on this. So for example, if I put P here, so they've called this, they've given us the general coordinates A sec theta, B tan theta. Okay, so I've got a point down there. And then they've got the line rather, joining that to the focus. Now the focus is going to be on this side of the hyperbola, and the other focus will be here. The focus, if you remember, is what the hyperbola or the parabola or whatever, it bends around, its curvature is around it. So apparently that line joining that point to our focus is parallel to one of the asymptotes. So I'm going to draw it in sort of like this. Okay. All right. So there is the focus there. What are the coordinates of the focus, by the way? I think they're A, E, 0, aren't they? Okay, so we've got that. Let's keep going. This is just a standard hyperbola. X squared on A squared minus Y squared on B squared is equal to 1. Now, there's this line joining P to the focus, and it's parallel to an asymptote. So I'll just stick some arrows on there. Show that the asymptote, the directrix, and the tangent at P are concurrent. Wow, okay, so 3 different things, right? So there's another tangent here, or there we go. So there's a tangent at P. This is the tangent at P. And they're saying that this tangent, that asymptote, and the directrix, which I suppose would go through here. Okay, that's the directrix. Okay, they're suggesting that they all pass through the one point there. That's what it means that they're concurrent. Okay, is that right? So, being that that's the point of intersection we're looking for, I'm just going to call that I for intersection. Okay. So how do we go about starting this? In some ways, this is really just showing that a bunch of equations are going to satisfy, a bunch of coordinates are going to satisfy a bunch of different equations, because that's what will give you concurrence. Okay, so I need to work out what all of these pieces are. So I think my starting point is actually going to be SP, that line there. I need to know what its equation is, because then I can work out all the other pieces that relate, because in some ways that line is what's important, okay, because they define that as parallel to the asymptote, okay? So I'm thinking about line SP right now, okay? Now I know it goes through the focus, right? So I've got 2 coordinates, and I also know it's parallel to the asymptote. Now, I've drawn 2 asymptotes. The equations for each of the asymptotes are plus or minus B on A x, right? They pass through the origin, okay? So being that this one is the positive one, its equation must be B over A times x. That means its gradient has to be just B over A, okay? So therefore I can use point gradient form to express the equation of SP, okay? So y minus y1, well, it passes through the focus, so I'll go y minus 0 equals, we just established that the gradient was B over A, and then I've got x minus AE inside the brackets, because that's what my x coordinate is, okay? Now, if I solve this together with the equation of the hyperbola, which is over here, okay, then that should give me the coordinates of P, because that's where they two intersect, okay? Now, sorry, I've just tidied that up a little bit. Don't need that 0, I suppose. Okay, so let's go ahead and try to solve it. This is the equation, by the way, x squared on A squared minus y squared on b squared equals 1. So I already have y as a subject here, so I might as well just sub it in, okay? So I'll get x squared on a squared minus, okay, here's my y squared, so it's b squared on a squared x minus ae all squared. That's my numerator there, that's y squared, okay? And that's all over b squared, and that's equal to 1. Okay, what can I do with this? Well, it's kind of nice that those b squareds cancel. I've got x squared on a squared hanging out the front, right? But then I've also got, you can see I actually can multiply through by a squared, can't I? Okay, because I've got a 1 over a squared there, x minus ae all squared. That's 1. Okay, so we'll keep going. I don't even know if I'm in the shop or not, so we'll just move this down a little bit. Okay, can we solve a little bit? What did I suggest? Multiplying through by a squared. So that'll give me x squared minus x minus ae all squared is equal to a squared. Okay, let's expand. X squared minus 2aex plus a squared e squared equals a squared. Okay, so expand those brackets, just be careful for that negative. So x squared minus x squared plus 2aex minus a squared e squared equals a squared. Cancel, cancel. And what am I after? I'm solving these two simultaneously. So I just want the x coordinate, don't I? Okay, so I'll just rearrange a little bit. I'll kick over that a squared e squared to this side. A squared plus a squared e squared. And then I guess I'm going to divide by 2ae, which gives me, factorize that a squared out. 1 plus e squared there. There's a 2ae there. One of the a's will cancel here. So I get a outside of 1 plus e squared all over 2e. Okay, so what have I got? I've got the x coordinate of this point here. Okay, now it doesn't take too much work. You can go ahead and do the algebra. I think you guys will be fine. If that's the x coordinate, if you sub that back into our equation here, you get a y coordinate as well. And you should end up with, if you do your numbers right, because I worked this out earlier, b outside of 1 minus e squared on 2e. Okay, so now this gives me the coordinates of P. Now the reason why I need the coordinates of P is because that'll allow me to work out what the equation of this tangent is. Okay, so what's the equation of a tangent to the hyperbola, being that it's this kind of hyperbola, just in general form. Okay, what's the equation of the tangent? We actually learn a standard form for this, right? So the tangent will have an equation in the form x(x1) on a squared, y(y1) on b squared, and that's equal to 1. Okay, so now I can go ahead and I can actually stick in these points, and I'll get, let's see here, well there's an a there and a b there, and they'll cancel with an a and a b there. So I think you're going to get x outside of 1 plus e squared on 2ae, because you'll have one of the a's left, and you'll get the same thing here except with the equivalent terms for y. Now all of this, like, this is mostly just algebra right now, but there you go, there's the equation of the tangent. It looks a bit messy. We could probably make it a bit neater, but it's fine. All I need is that that's the actual equation. Okay. All right, now let's just come back here. Now, I've got the equation of the tangent now, okay? If I can show that the tangent goes through where the asymptote and the directrix intersect, then I'm done. Okay? So all I need to know is, well, okay, where does the asymptote intersect with the directrix? Okay, we left this off before. That was the equation of the asymptote. What's the equation of the directrix? If that's AE, it should be x equals to a over e, right? Because we're on the right hand side. Okay, so it's really easy to work out where the directrix and the asymptote intersect, because they're just straight lines, right? So I should have, let's see, if x equals a over e and y equals b on a x, then y is equal to b over a times a over e, which is b over e. That's the y coordinate. And you can stick that back in and you'll get x being a over e. That's quite easy to determine. Okay, so that gives us, that's what I'm calling, I called it I, capital I earlier. That's the point where the tangent, the asymptote and the directrix intersect. Is that okay? Okay, so that's the coordinates of I, where directrix and asymptote intersect. So now what I need to do is I need to put these coordinates into the equation that I had for the tangent, which looked like this, which I know looks awful, but actually the symmetry of it will work in our advantage. So maybe if I put that there so we can see it, maybe I need a new piece of paper. Okay, here we go. So I'm going to take x equals a over e and y equals b over e, and you just got to be careful because you're not going to sub it into this equation because then you've got left hand side and right hand side both there. I want to prove that the left hand side will be equal to the right hand side if I take these values. So I'll literally say left hand side. That's going to be, well, x is a over e times 1 plus e squared, all divided by 2ae, minus b over e is my y value, 1 minus e squared, all over 2be. Okay, what's this equal to? A cancels here, b cancels there. That e is going to come onto the denominator, isn't it? So in both cases. So I've got 1 plus e squared on 2e squared. And then I've got 1 minus e squared on 2e squared. You can see what's happening, can't you? Because that's going to be 1 plus e squared minus 1 plus e squared, because I'm just, watch out for that double negative. That's all over 2e squared. So you get 2e squared all over 2e squared, which is 1, which is the right hand side that I wanted. So therefore, those coordinates, I, that satisfies the equation of the tangent. So that means it's on the tangent. And don't forget that this is where the asymptote and the directrix were intersecting in the first place. So that means they all pass through the one spot, so they're concurrent. And that's it.